This video is brought to you by mywayteaching.com.
In this part, let us study field due to a uniformly charged infinite plane sheet. Okay, let sigma be the uniform surface charge density of infinite plane sheet. Okay. As you can see in this figure, we take the x-axis normal to the given plane. By symmetry, the electric field will not depend on y and z coordinates. Its direction at every point must be parallel to E. We can take the Gaussian surface to be a rectangular parallel pipe of cross-sectional area A. As shown, as seen from the figure, only two faces 1 and 2, you can see here, will contribute to the flux, and the electric field lines are parallel to the other faces and therefore they do not disturb to the electric flux. And the unit vector normal to surface 1 is in minus x direction, while the unit vector normal to surface 2 is in plus x direction, isn't it? So the flux E dot delta S through both the surfaces are equal and add up. Therefore, the net flux through the Gaussian surface is given by 2EA, and the charge enclosed by the closed surface is sigma into A. Okay. So 2EA is equal to sigma A by epsilon naught, or in other words, E is equal to sigma by 2 epsilon naught vectorially n cap, where n cap is a unit vector normal to the plane and going away from it. And this electric field E is directed away from the plate if sigma is positive and towards the plate if sigma is negative. And E is independent of x also. So for an infinite large planar sea, this equation of E is approximately true in the middle regions of the planar sheet and away from the ends. Field due to uniformly charged thin spherical shell. Again, let sigma be the uniform surface charge density of a thin spherical shell of R. And here the situation, it has spherical symmetry. The field at any point P outside or inside can depend only on R and it must be radial. If you consider field outside the shell, then consider a point P outside the shell with radius vector R. Okay. As you can see, with R greater than R and R less than R. Outside the shell is the first case and inside is the second case. So we are considering point P here outside the shell with radius vector R. To calculate E at this point P, we take the Gaussian surface to be a sphere of radius R with center O passing through point P. And the electric field at each point of the Gaussian surface has same magnitude E and it is along the radius vector at each point. So E and delta S at every point are parallel and the flux through each element is given by E into delta S, and the flux through the Gaussian surface is given by E into 4 pi R square. And the charge enclosed is given by, so the charge enclosed is given by 4 pi r square, and by Gauss' law, we can write E is equal to by Gauss' law, E into 4 pi r square is equal to sigma by epsilon naught 4 pi r square, and E is equal to sigma r square by epsilon naught r square, isn't it? And here Q is equal to 4 pi r square into sigma is the total charge which is enclosed. Okay. And vectorially, if we want to represent E, then we can represent it as 1 by 4 pi epsilon naught Q by r square r cap. The electric field is directed outward if Q is greater than 0, inward if Q is less than 0. Okay, this is the field produced by a charge Q placed at the center O. For points outside the shell, the field due to uniformly charged shell is as if the entire charge of the shell is concentrated at its center. And for the second case, if we consider, that is field inside the shell, so the point P you can see here, it is inside the shell and the Gaussian surface is again a sphere through P and O as the center. And the flux through the Gaussian surface is given by E cross 4 pi r square as calculated before. And here the Gaussian surface encloses no charge. So this it gives E into 4 pi r square 0. If E is equal to 0 for r less than r, that is the field due to uniformly charged thin shell is 0 at all the points inside the shell. Okay. So the experimental verification of this result confirms 1 by r square dependence in Coulomb's law. Okay. Now let us study one simple example. An early model for an atom considered it to have a positively charged point nucleus of charge Ze, which is surrounded by a uniform density of negative charge up to a radius r. The atom as a whole is neutral. For this model, what is the electric field at a distance r from the nucleus? Okay. At this point, we should find the electric field, point P. The charge distribution for this model of the atom is as given in this figure. The total negative charge in the uniform spherical charge distribution of radius r must be equal to minus Ze, since the atom is neutral. And this immediately gives us the negative charge density rho, isn't it? So that negative charge density rho, so we must have 4 pi r cube so rho will be equal to minus 3 Ze 4 pi r cube. To find the electric field at a point P, which is the distance r from the nucleus, we use Gauss' law. Because of the spherical symmetry of the charge distribution, the magnitude of the electric field depends only on the radial distance, whatever may be the direction of r. And its direction is along the radius vector from the origin to the point P. And the obvious Gaussian surface is spherical surface centered at the nucleus. Here we consider two situations. So first situation, R is less than R, and the second is R is greater than R. So for the first case, the electric flux enclosed by the spherical surface is given by pi is equal to epsilon R 4 pi R square. Okay, it is the epsilon ER. This is the magnitude of electric field at R, isn't it? This is because the field at any point on the spherical Gaussian surface has the same direction as the normal to the surface there, and it has the same magnitude at every point. And the charge Q enclosed by the Gaussian surface is the positive nuclear charge and the negative charge within the sphere of radius R. So if you consider Q, it is negative as well as positive charge which is enclosed there. Four pi R cube 3 rho. And substituting for the charge density rho, here the value what we have calculated earlier. Okay, and here you can simplify this. We get ZE minus ZE R cube by R cube, isn't it? And Gauss law then gives epsilon R is equal to ZE 4 pi epsilon naught 1 by R square by 1 by R cube for R less than R, and the electric field is radially outward. For R greater than R, in this case the total charge enclosed by the Gaussian spherical surface is 0 since the atom is neutral. And from the Gauss law, epsilon R 4 pi R square in this case is 0, and epsilon R is also equal to 0 for R greater than R. At R is equal to R, both cases give the same result, that is E will be equal to 0.